All right, so what we have now is a little bit of work to do reviewing slopes, parallel lines, perpendicular lines, and so on and so forth. So let's do a little stop and start here, but let's do them one at a time. So we're going to do stop and start just for number one. Don't do 2, 3, and 4, just number one. Go ahead. Okay, so what you should be remembering here is that parallel lines have equal slopes. So if the slope of a particular line is 2/3, the slope of a parallel line is also 2/3. What about the slope of a perpendicular line? Well, what you need to remember with perpendicular is it's the negative reciprocal. In this case, it's a positive slope, 2/3, so you're going to have to make it negative. And the reciprocal means to flip the fraction upside down, so that becomes -3/2. So my answer is -3/2. So when you do the perpendicular line, you always negate. So if the original line is a positive slope, you're going to get a negative. If the original line is a negative slope, you're going to get a positive, and you always flip the fraction, okay? So if the original slope was 5/7, you're going to get 7/5. If it was -5/7, if it was 5/7, you're going to get -7/5. And if it was -5/7, you're going to get +7/5. Okay, so try number 2, a little stop and start. Okay, so it says the slope is -4/3. So a parallel line is also -4/3. A perpendicular line, negate it, so you know now it has to be positive, and flip it 3/4. What about the slope of a line is -3? Do number 3, stop and start. Okay, so, and remember also that -3 is really -3/1. So the slope of a parallel line is also -3/1. Now, granted, like if this was multiple choice, I think it's highly likely the correct choice would just say -3 and not -3/1. But I think it's important that you remember that it's really -3/1, because when we do the slope of a perpendicular line, we know we have to negate that to make positive, but we also have to flip that fraction. So, oh, look at that. I made a mistake on that. It should be +1/3, not negative. I'm going to correct that on my paper, and maybe that will help you remember to correct it as well. Okay, so that was 1/3. I didn't run a beta test. And see what happens when you don't run a beta test. All right, there we go. Filling in all the answers. And 1/3, that's the correct answer there. Okay, so then number 4. What is the slope of a line parallel to y = 4? Well, parallel means it has the same slope. What is the slope of y = 4? Well, it's really y = 0x + 4. Remember that for parallel and perpendicular. Go ahead, a little stop and start. Okay, so parallel to y = 4 is 0, because as we just mentioned, it's really y = 0x + 4. There are no x's, and that means there's 0 x's, okay? And perpendicular, well, it's interesting. Perpendicular takes 0 from the numerator, puts it on the denominator, and that's what we call undefined or no slope. Think about it this way. Y = 4 is a perfectly horizontal line. Perpendicular to that is a perfectly vertical line. And as we've mentioned several times, perpendicular, a line that is perfectly vertical, has no slope or an undefined slope. Okay, let's do a little stop and start also with this question. Graph the line 3y - 2x = 6 using both the slope-intercept form and by graphing the intercepts. So stop and start the video, graph that line, and then we'll go over the correct answer to it. Okay, I think you've had the time necessary. So first we'll go over how to do it with the slope-intercept. I start with 3y - 2x = 6, but the problem is it's not in y = form. So this is just like solving literal equations, which we practiced a whole bunch. Add 2x from both sides. I get 3y = 2x + 6. Divide everything by 3, and I get y = 2/3 x + 2. Which means the slope is 2/3 and the y-intercept is 2. Okay, so this is, I didn't cross out the 3's, but what you're left with is y equals 2/3 x and 6/3 is 2. So that's your slope-intercept form, generating that the slope is 2/3 and the y-intercept is 2. Now, as far as the graphing intercepts form goes, we always just start with the original equation, and then we plug in a 0 for x, that gives us the y-intercept. We plug in a 0 for y, it gives us an x-intercept. 0 always goes for the opposite. So if x is equal to 0, then that means 3y is equal to 6, right? Because if x is 0, negative 2 times 0 is just 0, and the whole term drops out. So if 3y is 6, that means y is 2, dividing both sides by 3, so the y-intercept is 2. If y equals 0, that means the y term is going to drop out, because 3 times 0 is 0, and I'm left with negative 2x is 6, dividing by negative 2, I get x is negative 3. So the x-intercept is negative 3. So when I go to graph this line, I'm going to start by graphing using intercepts. First, I graph the y-intercept. That's 2. I put the value up there. Then I graph the x-intercept. That's negative 3. And then I simply connect the dot. Now, what if I'd have chosen to graph it using the slope-intercept form? Well, I'm going to begin at 2, which I have right here on my graph, and then I'm going to go up 2/3, and then again up 2/3. And this, the one on negative 3 on the x-axis, that's just a continuation of the line filling in the backside. So either way, I come up with the correct solution to that. All right. Now, what about the slope as a rate of change? Okay. When I consider the slope as a rate of change is just another word for slope. It's how quickly things are changing. Slope is defined as the ratio of change, how quickly it's changing, in y to a corresponding change in x. In other words, the change in y over the change in x. It tells you how fast the y is changing with respect to the x. So the slope, thus the slope of a line is its rate of change. All right, so the slope is rate of change. It's the same exact thing. It has become common on tests nowadays to ask, instead of find the slope, which is what everybody asked for many decades, if not centuries, they now ask to find the rate of change. Now, how might they typically do it? They might typically do it as it is in this question. A little real-life application. Use the ordered pairs in the figure shown to find the slope of the line segment that represents men. Express the slope correct to 2 decimal places. Of course, we can convert slope to a decimal. We don't usually, but we can. And describe what it represents. Now, I'm going to change this question slightly. I'm going to ask you first to find the rate of change for women, and then second for men. That way we get 2 chances to practice it, okay? So let's have you try right now to find the rate of change of the number of U.S. adults, in this case women, ages 18 and older that live alone. And we're looking for the change from 1990 to 2008. Go ahead. Okay, assuming that you did stop and start, we know that change slope or rate of change, and we abbreviate rate of change ROC, is the change in y over the change in x. You could also use the formula y from the second point minus y from the first point, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, which is x from the second point minus x from the first. So my y is 18.3, and there's 14. And my x's are 2008 and 1990. So what we have here is, if I go 18.3 minus 14.0, the change in the y, over 2008 minus 1990, the change in the x, I get 4.3 over 18. I divide by a decimal, and I get 0.24, because it said round to nearest hundredth, 2 decimal places. So there are 0.24 more women living alone per year since 1990. Not more than men, but more women compared to what women used to do in living alone. All right, so again, the process is to subtract the y's over, subtract the x's. You get a fraction, convert that to a decimal, and then interpret it, what it represents. And it's simply put going to be more women living alone per year since 1990. Okay, let's have you try the next one, which is just to do the men. Same exact question, but now you're going to do the second line, the line on the bottom, the one that represents men. Okay, a little bit more. Stop and start. Okay. So the men, the rate of change in y over change in x. Okay, this time it's 14.7 minus 9.0 over 2008 minus 1990, which gives me 5.7 over 18, which is 0.32 more men compared to men in the past living alone since the year 1990. So we can tell men and women, people as a whole, are living alone more frequently. Okay, now some real life examples of where rate of change might be used. Okay. One is determining the pitch of a roof. Now, I built the house. Well, I didn't. I paid someone to build a house for me. In October of 2019, it was finished. So it started in 2018, finished in 2019. And pitch of a roof was a big deal. My oldest son really didn't like math very much. And he used to shake his head because he wound up going into carpentry. And he says, I can't believe it. All that math I really didn't like very much. And I wound up using it all the time with pitches of roofs and stuff. His girlfriend is a great snowboarder. And when you construct slopes for snowboarding, there's certain angles or rates of change of the slope, bottom to top, that are going on. If you build a wheelchair ramp, or in the case of one of the things I'm going to be doing tomorrow is and the next day is renting a couple of tools. I'm going to rent what's called a ditch witch for digging a trench to run some electric to a garage that I just had built. And I also need a stump grinder to grind up some stumps. So these things we have going on there. So that's where you would need to know the rate of change. Another example is stairs in a house, right? You don't want that rate of change changing. Then the stairs, you might trip on them. And last but not least is when you analyze data and you put the data on a graph. You might need to know what the rate of change is. So all of those situations and all of those circumstances are times and places where rate of change becomes a big issue. And we will ask you a number of times during the rest of the year to compare rates of change. And all you need to remember is change in y over change in x. Subtract the y's over subtract the x's. Go in the same order. That's that sub 2, sub 1 stuff. And that'll get you your values.